Welcome back. So last time we talked about star birth. We talked about how the stars are formed from that initial cloud of gas and dust. Now we're going to talk about how they die. And there's really only a couple of simple rules that you need to remember. And once you've remembered those, you can apply them and tell how the star is going to move on the HR diagram and figure out it's going to become a giant, a supergiant, and all these other sorts of things. So look at the rules and then follow along with your worksheet and see if you can figure out how is the star going to change. If you can understand and predict how it's going to change, you're going to be a long way towards memorizing each of these steps. Let's get started. All right, so as I said, we're going to be talking about star death, so make sure you've got your class notes out. Looks like this. The practice then is going to look like this. It's going to look very familiar based on what we do in the lesson, hint, hint. So we're going to talk about the death of stars, but we're going to break them down into two classes. We're going to talk about high mass versus low mass stars because they're going to die in a little bit different way. We're going to define a low mass star to be anything from 0.08 solar masses, remember that's the smallest possible star, to 8 solar masses. And then a high mass star will be anything bigger than 8 solar masses. Now, I gotta say, if you take any advanced astronomy classes or you take graduate school classes, things like that, we actually use different breakpoints for high, intermediate, and low mass stars. For our purposes, we're going to choose this because 8 solar masses is when a star dies as a supernova in this colossal explosion, the largest explosion in the universe. Anything less than 8 solar masses will not become a supernova. Our sun is obviously 1 solar mass, so it's not going to die in a supernova in spite of what you may have heard. So we're going to talk about how will that star die. So let's pick up from there. So here's those rules that I mentioned. The first rule is whenever I have ash, it's not really ash like leftover when you burn something, it's non-fusing material. Builds up, whenever that builds up in the core, convection takes over. Let me explain what convection is. Convection is kind of like a lava lamp, if you've ever seen one of those. It's got this, container with some goo in it and a heating element in the bottom. Whenever that goo is near the heating element, it heats up and it starts to rise. But as it gets farther away from the heating element, what happens to its temperature? It goes down. Well, as the temperature goes down, it starts to sink. It gets more dense. Then it gets closer to the heating element and it heats up and it starts to come up. So this rising and sinking action is convection. Another place you may have seen this is if you're looking at the heater from your car. Hopefully, you're not feeling the direct heat from the heating element in your heater. That would be uncomfortable. Instead, what that does is it heats up the air, which then gets blown through the vents and blown into your face to warm you up. That's convection. Anytime we're using air or some sort of gas to carry the heat, as opposed to just like feeling the radiant heat like from a campfire or something, that's what we're talking about with convection. Well, whenever this convection dominates, and there's a little bit of convection in all the stars, but whenever it dominates, it blows the star up like a balloon. And that's actually a really good analogy. If I take a balloon and I blow up into it, it's not the heat of my breath that's making it expand. It's actually the pressure of the air pushing against the rubber of the balloon that makes it expand. And that's literally what's going on with these stars. They're getting really huge because those convection cells are pushing on the outer layer of the star and making it get bigger. So the second thing you need to keep in mind is whenever a star expands, and we're talking about the envelope, when it expands, the atmosphere is going to get cooler. When it shrinks, the atmosphere is going to heat up. This you may have experienced before if you've ever seen the canned air, like you use spray air that you use for cleaning your computer keyboards and things like that. If you've ever taken one of those things and just held down the trigger and sprayed the daylights out of that thing until it's completely empty, what happened to the can? It got really cold because what happened was all that gas was compressed inside that can. When you release it, it expanded to fill almost the same size as your room. Well, when it expanded, it cooled down, and so the can got cold as well from that. All right, so let's start with a low mass star. It's been sitting here fat, dumb, and happy on the main sequence for about 10 billion years, happily, stably fusing that hydrogen into helium. The helium can't fuse, and it's heavier than the hydrogen, so it sinks down into the core. Starts out with just a little bit, and then more and more start to build up. The pressure in the star is not high enough to fuse the carbon, so that helium ash builds up. It fuses the helium into carbon, So that helium ash builds up in the core. And as it builds up in the core, then eventually we're going to get enough of it that convection is going to dominate. Think about your rules. What happens to the size of the star when convection dominates? It blows up like a balloon. It gets really big. Well, as that star gets big, what happens to its temperature? It decreases. So here's an example. That's the star is going to get cooler. So is it going to be red, blue, yellow, what? Cooler things are going to be red. And because it's big, it's going to be a giant. And so we call this the red giant phase. And here you can see in a normal star, in a solar type star, then there's just a small area where I have convection. Most of the star is actually dominated by radiation, like campfire feeling. However, in a red giant, almost the entire star is convection cells. So it's blowing it up like a balloon and making it really big. Here's a comparison picture. Here's the sun right next to this red giant to give you an idea of the size this thing gets to. All right, so we know that the envelope is getting bigger. We know that the envelope temperature is decreasing. Pause the video and figure out how does the star move on the HR diagram. Hopefully you pause the video, because remember, things are going to get more and more complicated. You need to take the time to think about it so that it don't just sit there and kind of let it wash over you, or else you're going to get lost. All right, well, the envelope size is increasing, but we talked about how the smallest things are down here and the largest things are down here. Remember that when we're talking about the HR diagram. So we know it's going to move in this direction, and the envelope is temperature is decreasing, so that's going to move it down as well. So the star is going to move into this area here, and that is why this is the giant region that we studied when we were first talking about the HR diagram. And you don't have to memorize this, but the sun will spend about 100,000 years. Things don't stay as red giants for very long. So just to give you a comparison then, this is the sun, and this is Arcturus, which is a red giant you can actually see in the sky. It's much cooler than the sun, but it's much bigger. And since it's so big, it actually is fairly bright out in the sky. All right, so that non-fusing core, that helium in the core, that ash, is not going to, it's going to continue to collapse. Why? Think about hydrostatic equilibrium. The only thing that can stop the collapse is if it's generating energy. Well, it is generating a little bit of heat, but that's not enough to stop the collapse as it comes down. So eventually, it'll continue to collapse, and that pressure will get higher and higher and higher until it can fuse that helium into carbon. So at this point, it is stably fusing the helium into carbon. So there's no more ash, so convection no longer dominates. So if convection no longer dominates, what's going to happen to the size of the envelope? Well, now it's going to start to shrink. It's exactly like you had taken that balloon and just opened up the nozzle, the throat on it, and just let that air out. The balloon's going to get smaller. Well, as the envelope gets smaller then, what's going to happen to the temperature? Think about your rules. The temperature is going to go up. So what we end up having is a smaller star that's actually hotter, but I'll have a core here where the helium is fusing into the carbon, and then just a shell of hydrogen that's fusing into helium on the outside surrounding that core. So this hydrogen fuses into helium, the helium drops down in the core and starts fusing into carbon from that. So the envelope gets smaller because convection has stopped or decreased, is no longer dominating. The temperature has increased because the star has shrunk. So pause the video. How does the star move on the HR diagram? Well, if the size is getting smaller, it has to go this way, and if the temperature is increasing, it's got to go this way. So it drops down to about right here. And we call this the horizontal branch. The key thing about the horizontal branch is that it is stably fusing helium into carbon. It is not a main sequence star, even though it's stable, because remember, to be a main sequence star is to be stably fusing hydrogen into helium. But it is stable, and so the sun will spend quite some time here, 50 million years or so. Now that's nothing compared to 10 billion years, but it's a lot more than the 100,000 years it spends as a red giant. So the reason we call this the horizontal branch, it doesn't move horizontally here, but we started out with the sun here. If I had a smaller star here, it would land maybe over here, and this star might land over here, and this star might land over here. So when they're all stably fusing the helium into carbon, they end up being on a line right here. That's kind of like the main sequence, except it's horizontal. Now, over time, we start to build up more and more of that carbon. And the carbon can't fuse. There's not enough mass to squeeze that carbon to fuse it into oxygen, which is the next stage in the chain there. So it drops down into the center as ash. So look at what's happening. We've got these shells here. And so the hydrogen is fusing into helium here. The helium, which is more, it's heavy, it's more dense, drops down into the next shell here where it gets fused into carbon, and then the carbon drops down into the center as ash. So think about your rules. What happens whenever we have ash building up in the core? Convection begins to dominate. So if convection dominates, then this is going to blow up the star like a balloon, except it's going to get really big this time because we're running at temperatures where we're fusing helium into carbon. So it doesn't just get big, it gets really big. And so think about it then. The size of the envelope is going to get much bigger. So what's going to happen to the temperature? Well, if the envelope gets bigger, then the temperature is going to go down. So we call this an asymptotic red giant. And yeah, that's kind of a funny word to say, but asymptotic just means it approaches. And so what's happening is it's approaching a supergiant. And if it were allowed to live long enough, it would actually reach a supergiant size. But because this phase doesn't last very long, it never actually reaches quite up that high. So we kind of separate it out from the supergiant that we're going to talk about later and refer to this as an asymptotic red giant. But the big thing to think about is it's a really big red giant. So we've said that the envelope size increases, the envelope temperature decreases. So pause the video. How is the star going to move on the HR diagram? Okay, did you think about it? All right, so the envelope size is increasing, so it's going to move this way. And then the temperature is decreasing, so it's going to move this way, so it pops up here. And you see that we're just barely in the red giant area. And in really extreme cases, it can actually get up here towards the supergiant area. But because, again, it's not going to last very long for this low mass star, only about 10,000 years. So there's not time for it to get really big. So here's a comparison. This is Arcturus that we were looking at before. Sun is maybe about this big. So when the sun reaches the asymptotic red giant phase, it swells up to be really big. And at this point, it's eaten its children. Tasty. So Mercury, Venus, Earth, and Mars are all inside the star. So the orbit of Mars might be, right about here. The sun is only going to be a small little dot right about here. And Aldebaran is another star that you can see with your naked eye. It's not terribly hot, but it's very bright just because this thing is so friggin' huge. So Aldebaran is a good example of an asymptotic red giant. Star the size with the mass of the sun will never have enough mass, will not have enough squeezing power to force that carbon to fuse into oxygen. It'll just never happen. So what happens then, that ash continues to shrink. It continues to collapse, that carbon. And eventually it falls into something called electron degeneracy. Now this is not a quantum mechanics course. We're not going to get into a whole lot of details about it. What I want you to think about, when you think about electrons, you can think of them as being marbles. And as long as they aren't touching each other, everything's fine. They never intersect. But eventually, if we squeeze hard enough, those marbles, those electron marbles actually touch each other. That's degeneracy. That stops that collapse. However, degeneracy in the presence of fusion makes the fusion temperatures go crazy, makes them go wild. So we get this huge burst of energy whenever these things touch because fusion is taking place all around it. So that causes this big rush of energy, which makes the core expand a little bit and makes those electron marbles move away. Well, now it stopped the degeneracy, so it starts to fall back. And that energy comes back and it pushes it back out. In the envelope of the star then, if the energy increases, what happens to the size of the star? It gets really big, but then those marbles, those electron marbles aren't touching anymore. The energy goes down. What happens to the star? It gets small, and then they touch, and it gets big, and then they back and forth and back and forth. So the star starts to pulse. It becomes unstable, and it starts to pulse like this. So it pulses in both size and luminosity because obviously it's bigger, and then it's cooler though at the top of the pulse, at the greatest extent of the pulse. Well, eventually it will get cool enough on the outer parts that molecules can actually start to form. Well, when molecules form, they release energy because they're more stable. So it gets pulse, 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 and then it releases a little bit more energy, which gives it a kick, and it puffs the outer layers out into space. And it's a very gentle kind of puff. So that's what's happened here. This is called a planetary nebula, which is unfortunately one of the most misnamed things in astronomy because it has absolutely nothing to do with planets. They named it this way because we thought this was a solar system in the process of forming. We now know that this is actually the other end. This is actually a star that's just died. So all of this material you see here is actually the envelope of the star. The core of the star is what the arrow is pointing to right here. That's all that's left of the core, but we can now actually see the core. So the star is in two pieces. We call the envelope a planetary nebula. That's also the event in which it dies. The core then we call a white dwarf. And you ran into some classifications with that before. It's white, which tells you it's really, really hot. But let's think about this. This core was at 60 million degrees when it was fusing. Is it fusing now? There's nothing squeezing it. The fusion stops almost instantly, in astronomical terms anyway. So is it still a star? If it's not fusing, it's not a star. So a white dwarf is not actually a star. It's the burned out core of a star. So fusion has stopped. So the temperature drops rapidly from 60 million degrees to maybe 30,000 degrees. Huge plummet. But it's going to take a while for it to radiate out that remaining 30,000 Kelvin or so. Think about it. This thing is made out of almost entirely carbon. If you've ever had a grill, backyard grill or whatever, where you've used charcoal briquettes, those are almost entirely carbon. Well, when you turn the flame off, those bricks don't cool down immediately. They take a long time for them to cool down. Same thing is happening with this core. It is slowly cooling down. And as it cools, those electron marbles gently settle down on top of each other so that electron degeneracy keeps the core from collapsing any further, keeps that white dwarf from collapsing. And you may say, well, wait a minute, shouldn't that make it go crazy? There's no fusion anymore. So as long as there's no fusion, it's just going to sit nice and calm, and it's just going to hold itself together with those marbles stacked on top. So the white dwarf is supported entirely by these electron degeneracy. The white dwarf core is about the size of the Earth. So here we're kind of cheating a little bit on the HR diagram because the HR diagram is showing us the surface of the object, the star. But in this case, the envelope, which we've been looking at up to this point, has blown away. It's puffed out into space. We're now looking at the core. So now our HR diagram needs to plot the position of the core because the envelope is gone. Well, we went from a star that was this big down to something that's just the core. So what happened to the size? It went way down. In this case, though, the temperature went way up because that envelope was maybe, 6,000, 7,000 degrees or so. Now we're looking at the core, which is 30,000 degrees. So the envelope is puffed off. So even though it was cooler, we're looking at just the core. So we're kind of cheating just a little bit. But if the size gets smaller and the temperature goes way up, because we were looking at something that was like 5,000 degrees, 6,000, 7,000 degrees, now we're looking at 30,000 degrees. Where is this star going to be on the HR diagram? Right here. So this is the white dwarf area that we were looking at before. And then over time, it's just going to cool slowly down until it becomes a black dwarf. It's not radiating any heat at all. Here's some pictures of some planetary nebulae. They don't necessarily blossom out in this perfect ring like you've seen before. It just kind of depends upon what's going on, the convection currents and everything that's in the star itself. Here's the white dwarf. This is the envelope of the star. And keep in mind, this is not a violent thing. It's a puff as it moves out into space. A lot of the pretty pictures that you see are actually of planetary nebulae because they make such interesting patterns and colors. All right. So before we talk about high mass stars then, let's talk about low mass. Review our rules, summarize the low mass stars then. The low mass stars then are going to die in a planetary nebula. They're going to die with a whimper instead of with a bang. All that's going to be left behind is that white dwarf. So quickly reviewing our rules then before we talk about high mass stars. Again, if I have non-fusing ash in the core, the star expands due to convection. If it expands, then if the envelope expands, then it's going to cool down. If it contracts, the envelope's going to heat up. All right, so let's talk about a high mass star. So an O-type star might spend 10 million years on the main sequence. An A-type star like this might be a little bit longer than that, maybe 100 million years or so. But Even so, it is a main sequence star. It is stably fusing hydrogen into helium. So that helium then sinks down into the center of the core because it's not got enough pressure to fuse yet. Sound familiar? So what's going to happen when I start to build up that helium ash in the core? Well, then convection is going to take over. When convection takes over, then what happens to the size of the envelope? It gets really big. Well, as the envelope gets really big, what happens to the temperature? The temperature goes down. In this case, though, it started out big. So it gets even bigger and it moves into the supergiant region directly from the main sequence without going into this giant phase to begin with. Well, now these stars then, as that helium collapses then, it starts to fuse the helium into carbon. And so it can stably fuse the helium into carbon, and we'll start to build up carbon ash, and it gets bigger again when convection takes over. But eventually that pressure gets high enough, it can actually fuse the carbon into oxygen because it's got enough mass that it can squeeze that hard. And for the larger stars, it can fuse the oxygen into neon, the neon into magnesium, the magnesium into silicon, and the silicon into iron. Nothing can be fused beyond iron. Iron is the most stable element in the universe. It does not fuse into anything else, so that's where the process stops. So, but we call this an onion star because you see that all of these elements are being produced in this dying star. Other than hydrogen and helium, every element in the universe is produced in the heart of a dying star, including all of the elements in your body. You are literally star stuff. So, iron is the most stable element in the universe. Now, this is showing the amount of energy, the distance between the 2 points is the amount of energy you get. So as I go from hydrogen to helium, you see that I get a whole lot of energy. That's actually the most you can possibly get. As I go from helium to carbon, I get a little bit less. Carbon to oxygen, I'll get a little bit more. But iron, there's no way for me to go any further down. As I go this way, this is that fission we talked about. Uranium splits apart and breaks into lead, and it can eventually get all the way down to iron. But again, you can't break the iron apart and get any energy. So iron is the most stable element in the universe. It won't naturally fuse into anything else. In order to get iron to fuse, you have to add energy into it. So everything on the periodic table, if you've ever seen that, beyond iron had to have been created by adding energy into the object. And what happens is that's done in the process of a supernova. So that iron core is collapsing because there's nothing to stop it from collapsing. Those electron marbles touch, but there's so much mass, there's so much squeezing that those marbles actually break. And the electron gets forced down into the nucleus, it crashes into the proton and creates a neutron. Now we've got a core made out of nothing but neutrons. This is not even on the periodic table. We call it neutronium because it has no protons, it's just strictly neutrons. It's a big ball of neutrons. This stuff is so dense, has so much mass, so much gravity. A teaspoonful of this neutronium weighs the same as a battleship. The mass is so high it can warp time and space. It can produce gravity waves, all these crazy things. Those neutrons then collapse because, again, there's no energy being produced, nothing's fusing. Those neutrons collapse until they touch. And now they're being supported by neutron degeneracy. However, remember that degeneracy in the presence of fusion goes crazy. In this case, it's not just electron degeneracy, it's neutron degeneracy, which is even worse. These things touch, they rebound, and they blast back out into space. And one good way you can kind of simulate this, if you want to see what happens, take 2 racquetballs, little blue racquetballs, and do not stand over the top of them because it will hurt. But hold them directly above each other, and it takes a little practice to do this, but let them go at the same time. The bottom ball will hit the ground, and if you time it right, it bounces back up and hits this ball as it falls. That top ball will then shoot up and actually bounce over your house or something. You get an incredible amount of energy from that. The same thing is happening when this neutron degeneracy rebounds because of its degeneracy in the presence of fusion. The entire star blows itself apart. Supernovas are the most energetic explosion in the universe. We can actually see these happen at the edge of the universe. They're so bright. They can be brighter than all the stars, other stars in the galaxy put together. So this, what you're looking at here, is a supernova remnant. So this, in the middle, is that core that was left behind, and it's made out of nothing but neutrons. The rest of the star got blasted off into space. Now this nebula here, this supernova remnant, is enriched with carbon, oxygen, magnesium, iron, and everything in between, but also the materials beyond iron. So if you have a gold ring, gold is only created in supernovas. So that material in your ring was actually literally created in a supernova. And then this cloud then will eventually collapse and form a bunch of stars. Our sun is actually a third generation star, which is why we don't just have hydrogen and helium. If we were a first generation star with just hydrogen and helium, there wouldn't be any planets, at least not terrestrial planets. There wouldn't be any puppies, kitties, or you and me to talk about it. So by the time we've gotten to the third generation, there's enough of this other stuff that we can actually make things like life. So in 2016, we actually got lucky enough to watch one of these happen. This was actually an amateur astronomer. Astronomers have been trying to actually witness a supernova occurring as it occurs for a very long time, centuries. Nobody's ever pulled it off. And this amateur pulls it off on his first try. He had a new camera that he was testing. And so he was looking at this galaxy that you see right here. And then he noticed that there was a star, a bright spot that was appearing. That's actually a supernova. So this is a Hubble Space Telescope picture of the galaxy. It's 40 million light years from Earth. He managed to record within the first hour of the explosion. This is a Hubble telescope picture that was taken after his, where you can actually see the bright point. But this is his original data. And you can see that it's cycling through the pictures that he took. So here there's no star because it wasn't bright enough that you could see it. But then when that supernova occurred, it was so bright, you could see it even against the background of the rest of the galaxies there. So it's the energy from that supernova that's adding into the fusion that's fusing all of these higher elements. And so that's what you're watching occurring right here. So the type of supernova that we've been talking about today is a type 2 supernova, a core collapse supernova. The big thing is that it's formed from a single high mass star, and it's got a unique light curve. This is showing the brightness of the supernova. This is over days. The type 2 is the red. So we get this initial explosion, and then we get this flat line here as these other elements are being fused, and then they finally fade out as the fusion stops and it fades out. This second type is a type 1. Okay, so we discovered the type 1 first, but the type 1 is actually the collision of two white dwarfs. So if I've got a binary white dwarf and they come together, they can actually collide hard enough that they can fuse that carbon on the surface as a result of their collision from that. Well, remember, these things are being supported by electron degeneracy. What happens to fusion in the presence of degeneracy? It goes crazy. But now instead of being buried inside the star, it's actually on the surface. And so the star, both of these stars, both of these white dwarfs, blow themselves apart. And so that produces the second type that we'll be talking about later, called a type 1 supernova. Turns out, because all type 1 supernovas are made out of the same stuff, we can actually use this to measure the distances to different stars. And we'll be talking about that later on in the course. All right, so I want to quickly talk about the remnants from these high mass stars. The neutron star, remember, is made out of nothing but neutrons. It's got a very high magnetic field because as that star collapses, the magnetic field lines get closer and closer together, which means that they're much stronger. So those field lines enable any particles to get funneled out as jets. And so they're basically beaming out as radio waves. As these things rotate then, if that beam happens to sweep across the Earth, we get a radio pulse. Beep, 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 beep. When we first saw these things, they're very regular. It's one of the most regular clocks in the galaxy, in the universe, in fact. We thought that these were so regular they could not be natural. They had to have been made by aliens or something. So they call these LGMs, little green men. Later on, we realized, okay, no, it's just a rapidly rotating neutron star. But because they put out these pulses of light, you'll hear them referred to as pulsars. If I have a very high mass star, suppose that neutron star has a mass that's greater than 3 solar masses. So after everything's blown apart, I've got 3 solar masses of neutronium left over. So that means that original star had to be 15, 20 solar masses. Had to be huge to start off with. So if I have more than 3 solar masses in one place, then even neutron degeneracy can't stop the collapse. Those neutron marbles break. At this point, there is nothing in the universe that can stop the collapse of that star, the neutron star. So it's going to collapse down to size 0. Not very, very small, 0. So at this point, the gravity is so strong that light can't escape, and that's a black hole. And this is what you're seeing when we're talking about a black hole. This is the region from which light can't escape. The black hole itself is actually just a tiny point right in the center of this. There's nothing physical here, but we're going to be going into a whole lot of detail on this next week when I give you the famous black hole lecture. All right, so in summary then, for a low mass star, less than 8 solar masses, it's going to die as a planetary nebula. The core is going to form a white dwarf. The envelope will form the planetary nebula itself. The white dwarf is made almost entirely out of carbon, a few other things. The high mass star, anything greater than 8 solar masses, is going to die as a type 2 supernova. The core is going to be either a neutron star, and if that neutron star is greater than 3 solar masses, it'll collapse to a black hole. And just to remember that all elements heavier than iron, gold, uranium, platinum, everything, is made in that supernova when it's actually occurring. All right, so that's where we're going to stop. Make sure that you download the practice. You can use the video as a help. It shows you everything that you need, and follow through with this and then upload it, and then we'll grade it from there. So now we've talked about how stars die and the two different types, the low mass and the high mass. Next week, we're going to spend a little more time on the high mass stars because we're going to see how they die actually as black holes. And things bizarre happen when you're around a black hole. So time and space can change. You can get warp drive. You can get time travel. You can get all these kinds of things. So in next week's lesson then, we'll talk about exactly what happens and how all this works. So prepare to get your mind blown. We'll see you then.